All right, let's talk about something we all use every single day, but maybe don't think about too much: the actual physical cables that connect our digital world. We're going to go from the simple wire plugged into your computer all the way to the insane fiber optic lines that span the entire globe. We're demystifying it all.
So, have you ever really taken a close look at a network switch? That box with all the blinking lights in your office or maybe behind your TV? You've probably seen this little bit of text printed on it: 10/100/1000 base T. Looks kind of like a secret code, doesn't it? Well, stick around, because by the end of this, you're not just going to know what it means, you'll understand why it matters.
So that code, that's actually our way in. It's the key that unlocks the whole world of network cables. And we're going to start with the one I guarantee you've seen and used a million times. And the cable that actually plugs into that port, well, that's what we call a UTP cable. It stands for Unshielded Twisted Pair. This thing is the absolute workhorse of most wired networks, and if you could see inside one, you'd find, well, exactly what the name says: 4 pairs of little copper wires all twisted together. Okay, but why? Why are they twisted? It seems like such a random, small detail, but it's actually a pretty brilliant piece of low-tech engineering. Any guesses what that simple twist accomplishes? It all comes down to fighting off noise. See, the world is full of electrical signals flying around, and that can mess with the data in the cable. It's called electromagnetic interference, or EMI. That simple little twist in the wires acts like a shield, canceling out a lot of that interference. It keeps the signal clean, which means your connection is stable. Pretty clever, right? So we know why the wires are twisted, but what's actually going on inside that copper cable? How does your email or a cat video actually travel through that thing? Well, at the most fundamental level, everything you do online, literally everything, is broken down into a long stream of zeros and ones. We call these bits. Inside a copper cable, those bits are sent as little pulses or variations in an electrical signal. You can think of it like turning a flashlight on and off really fast to send a message. That's it. That's digital communication. But there's a catch with copper. That electrical signal gets weaker and weaker the farther it goes. It's kind of like shouting across a big field. Eventually, your voice fades out. For these standard network cables, that fading out point is right around 100 meters. That's the max effective distance. Okay, so we've got a cable and we've got a signal. But for two devices to actually understand each other, they have to agree on a set of rules. It's not enough to just shout, you have to be speaking the same language. In networking, we call these rules protocols. And this really is the perfect analogy. If you have one person who only speaks English and another who only speaks Japanese, they can both be talking, but nothing is getting through. It's the exact same with your computer and a switch. They have to follow the same rules, the same protocols, or it's just noise. So let's look at how this works in a normal situation, like plugging your PC into a switch. Inside that little plastic connector at the end of the cable, there are these tiny metal contacts called pins. By design, your PC is set up to send or transmit data on pins 1 and 2, and the switch, it's set up to listen or receive on those exact same pins. It's a perfect match. Everything just works. But that leads to a fun little puzzle. What happens if you try to connect two similar devices together with that same standard cable? Like, what if you want to connect one PC directly to another PC? Well, you run into a problem: a signal collision. Both PCs are trying to transmit, to talk, on the very same pins, 1 and 2. It's like they're both trying to shout into the same walkie-talkie at the exact same time. Nobody's listening and no data gets through. And the solution, back in the day, was actually pretty clever: the crossover cable. It looks the same on the outside, but inside, the wires are physically swapped. It connects the transmit pins from one PC to the receive pins on the other. So pin 1 on one end goes to pin 3 on the other, and pin 2 goes to pin 6. It's a simple, physical fix that makes sure one computer's mouth is wired directly to the other's ear. Now, you've probably never even heard of a crossover cable, right? That's because our devices got smart. Modern network ports have a feature called Auto MDIX. It basically senses what it's connected to and can digitally cross over the pins on its own if it needs to. It's like having a universal translator built right in, which has made these special cables pretty much a thing of the past. All right, that covers the world of copper. But what happens when you hit that 100-meter wall, or when you just need to go way faster? Well, that's when we stop using electricity and start connecting with light. Copper is great, for sure, but it does have those limitations. You've got the 100-meter distance cap, it can be susceptible to electrical interference, and let's be honest, our need for speed is always growing. Fiber optics was invented to solve all of these problems. And here's the magic trick. Instead of pushing an electrical signal down a copper wire, a fiber optic cable shoots pulses of light down a strand of glass that's literally as thin as a human hair. It's a totally different way of sending information, and it is incredibly fast and efficient. But, not all fiber is created equal. There are really two main types you should know about. First up is multi-mode fiber. It has a slightly wider core and usually uses a simple LED as the light source. The light kind of bounces around inside, which limits its distance. It's cheaper and perfect for connecting, say, different floors in the same building. Then you have single-mode fiber. This stuff is the real deal. It has a super narrow core and uses a powerful laser that shoots the light in a nearly perfect straight line. This allows the signal to travel for miles and miles. We're talking across cities. It's more expensive, but it's the champion of long-distance communication. So, we've got copper, we've got multi-mode fiber, we've got single-mode fiber. How in the world do you choose the right cable for the right job? This little chart really breaks it down nicely. Look, if you're just connecting your computer to a switch on the same floor, copper UTP is your go-to. It's cheap, it's easy, it just works. But the moment you need to connect two different buildings, you're in the world of fiber. For connecting buildings on the same campus, maybe a few hundred meters apart, multimode is a great, cost-effective choice. But if you're connecting offices that are miles apart, you have no choice. You need the power and distance of single-mode fiber. It's really all about matching the technology to the distance you need to cover. And that brings us all the way back to where we started. That secret code on the switch, 1000 base T. It's not so secret anymore, is it? Let's decode it. The 1000 is the speed, 1000 megabits per second, or gigabit speed. Base just refers to the type of signaling, baseband. And that T at the end, that tells you the type of cable it needs, twisted pair. Mystery solved. So now we know how we physically link everything up, from the copper in our homes to the light under the oceans. But that physical connection, that's just layer one. It's just the highway. The next big question is, what are the rules of the road? What are the protocols that manage this unbelievable global conversation that's happening across these wires every single second? But we'll have to save that for another time. Thanks for watching.